At this point you should be familiar with the concepts of ranges and sums. Sometimes though we want to take it a bit further and we want to use something a little bit more sophisticated than a range, and sometimes we want not just to sum systematically, but we want a constraint to be duplicated systematically. To illustrate these concepts, we're going to look at a case where we are going to transport a number of passengers, 3 different types, with 3 different types of vehicles. And our aim is of course to do this as cheaply as possible. Initially we are going to have to define what vehicles are available to us. And we could of course do this with a range, but if we do it with a set instead, we can also integrate the actual name of the vehicles into the representation of the set. What we are going to use to represent our 3 kinds of vehicles, buses, taxis and trucks, is a set of strings. A set of strings is declared like this. This is a set of string named vehicles, and we can, like with ranges, initialize it. Contrary to the sets you might know from mathematics, these sets have a defined order. Besides having to define the set of vehicles available to us, we are also going to have to define the set of items and persons that we are going to transport. This set we also represent as a string. We call the set to be transported, and we fill it in with cargo, passengers and wheelchairs. We now define how many of each we are going to transport. This is of course an integer, and we can call it needed capacity. We need one of these for each of the items to be transported. So we can use to be transported as we would have used a range. This will define an array, and we can initialize it like you have seen before. The interpretation here is that we have to transport 1000 items of cargo, 800 passengers and 20 wheelchairs. It seems obvious to us that a truck would be able to transport a lot of cargo but not very many passengers. So we have to specify for each of the vehicles how much of each category of items to be transported they are capable of actually transporting. For that purpose, I've predefined these numbers. We now have to encode this information into a parameter. As we are only working with integers, we need an integer type. Let's call it capacities. We need a set of capacities for each category of item to transport. And we need it for each vehicle. This double array will now be initialized. And if this confuses you, bear in mind that the line breaks here are inconsequential. The only one that is really consequential is the one with the semicolon. So this is just an array, and at each point in the array you have another array. So it's an array of size 3, and each item in the array is another array of size 3. So it's a double array. To interpret the data for the capacities, the first line can be interpreted as the cargo capacities of the 3 different vehicles. The next one is the passenger capacity of the 3 different vehicles, and the last one is the wheelchair capacity of the 3 different vehicles. The last parameter that we need is a set of costs, one for each of the vehicles, like this. Then finally what we're going to do is define the decision variables. So dvar as usual, and what we're going to decide here is how many of each of the vehicles are we going to use. So let's call that n used. But what type should it be? Well, it should be an integer, but when you think about it, it doesn't make sense to use a negative amount of vehicles. So let's make it a strictly positive integer, like this. And of course, we need 1 for each of the vehicles, like this. You should at this point be able to define the objective function yourself. We are not using any concept you have not seen before. We are simply minimizing, and what we are minimizing is a sum for v in vehicles, the cost of the vehicle, times the number of them we use. Of course, we also need some constraints on our decision variables. And what we're going to need of constraints here is we need a constraint for each of the items to be transported, because we need to make sure that we transport enough of each of them. The way we accomplish this is with a construct called Forall. It'll simply take approximately the same input as a sum, so we could say t in to be transported like this, and it will copy the following constraint for each possible way to select t in to be transported. The constraint itself is nothing new. What we're going to do is sum over all the vehicles. We're going to multiply together the vehicle capacity for the item we are currently looking at and the number of that given vehicle that we're using, that is the decision variable. This, of course, must be greater than or equal to the capacity we need. So if we take a look at how OPL Studio will handle this, this line will be duplicated 3 times. First, one for t equal to cargo, then one for t equal to passenger, then one for t equal to wheelchairs. If we take a look at the first instance where t equal to cargo, then what will happen with this line? What we'll do is sum over all the vehicles, that is trucks, taxis and buses. We'll take how many of that vehicle we use times that vehicle's capacity, in this case for cargo, and that should be greater than the sum of that for all of these vehicles should be greater than the needed capacity for cargo. These concepts I have just introduced are fairly important, so do take the time to understand them thoroughly. It might help you if you go and read through the transcript, as I provide a little bit more examples there and I explode it out. The model is now technically done, but there are a few concepts that I would like to introduce. If you paid attention, you might have noticed that I inserted brackets here. That's a way of explicitly telling that the scope of this for all includes this in here and only that. Should you wish to have more than one constraint under the same for all, you can also do that if you have the brackets here. You may also want to nest the for alls, so you could take this for all and you could duplicate it inside. Let's just fix the indentation here. Like this, and let's call this L instead. Now, this constraint that you put in here would be copied 9 times. 1 for each possible choice of T, and of which there are 3, cargo, passenger, wheelchairs, and 1 for each of these, 1 for each choice of L. And there are 3 of these, cargo, passenger, and wheelchairs. You can even set up a condition, like you could with sums, like you could demand that L not equal to T. If we pull out the stuff I just demonstrated, create a run configuration, add our model to the run configuration, and run it, we should get a solution looking something like this. That is, the set of decision variables is set to 9, 11, and 15. To interpret it, we can scroll up here and see that we use 9 trucks, 11 taxis, and 15 buses. This is easy enough to deduce here, but it can be a lot more complicated. So we of course have a remedy for that, but more on that in a later module.